We'll start off with the physiological mechanisms of palm cooling. Now, the palms, as well as the soles of the feet and the upper face that is above the beard line, are the optimal heat transfer interface, and this is the glabrous skin, which is characterized by the presence of arteriovenous anastomoses, so very dense vasculature, the lack of hair follicles, and just really unique anatomical and physiological profile for heat transfer. And they are really, really important and heavily relied upon in thermoregulation. And we can see that that has a positive effect when thermal stress is an issue. So the glabrous skin, the structure and purpose, it's distinct from all other skin regions of the body. Highly vascular, no hair follicles, and it's a thick epidermal layer, and there's deep sensory innervation as well. So a lot of the evolutionary roles, motor control, object manipulation, as well as primarily what we've seen is thermoregulation. And this is why you will see frostbite in your toes and fingers first. It's the same reason why we can cool our bodies down rapidly through our hands and feet. So some research done by Heller and Garan, and this is in 2012 out of Stanford, they were looking at glabrous skin versus other areas of the skin in relation to heat transfer. Now, heat transfer on the y-axis is per square centimeter, so it's relative to surface area. Now, what we see here are the black filled in dots are the rate of heat transfer for glabrous skin. And in this case, this is the palm and the face. Now, the palm being the squares, which is the highest, the face being the black circles, which is also high. A few things to note here, as opposed to, well, let me just call out the other ones. We have thigh, lower back, upper arm, abdomen, and upper back. Now, in resting state, so this is at the time in the bottom is with exercise onset. So in resting state, before any exercise, the rate of heat transfer is already significantly higher through the palm than other parts of the body. There is also a very strong response to exercise onset and to the new metabolic demands for drastically improved heat transfer and very quickly, whereas other parts of the body show very, very modest, very small responses and changes. This same concept from this same study is shown in a different diagram. You will see on the far right are the face and the palm. At exercise onset in white, it is significantly higher than the non-glabrous skins of the body. This again is heat transfer per area. But with exercise onset, it skyrockets, relatively speaking. So the hands, the glabrous skin, really are designed and optimized for maximum heat transfer per skin area, per surface area. A key feature are the AVAs, the arteriovenous anastomoses. So they're very dynamic vascular structures. They bypass capillary networks, so they're their own shunts, and they close and restrict. So vasoconstriction and vasodilation, very, very sensitive to temperature changes and can drastically increase blood flow through the hands. In fact, it can increase up to 16 times through cutaneous vasculature when in states of heat stress. So huge differences in total blood flow. What's also unique about them is they have large diameter. They can support large blood flow. They're typically constricted, but under normal thermoregulatory conditions, the hands and the feet are the primary mechanisms by which the body adjusts the internal thermostat under normal rest conditions throughout the day. Let's say you're in room temperature, and keeps you from going up and down, keeps you in that range. Now, the significance for heat stress is that when your body's overheating, you need to dump heat out of your body fast. Well, the body's response is to redirect a lot of blood to the hands and the feet, to these glabrous skin areas. This is also goes to the face, where we have a decrease in blood flow to the brain and more to the face. So these radiator-like surfaces have a lot of hot blood going to them. We now have an opportunity to dump heat through these interfaces, pass it out into the ambient environment, and it accelerates the rate at which we can get heat out of the body. And much like a car radiator, where you'd have the human body, let's say, is the engine of the car, the coolant would be the blood, and then you'd have the hands are the radiators, where you can dump the heat out, and then the cooler blood, the venous return, circulates back through the body, just like the coolant in a car. There has been a lot of research that started initially with the Stanford teams, Gran and Heller and the rest of the team at Stanford, finding that by cooling the palms during exercise, you could drastically reduce core temperature. You could extend time to exhaustion. You could increase endurance. And this will be the basis of the literature review we will do a little bit in this module and extensively in the next module. Now, the reason the palm is ideal for heat extraction covers everything we've just talked about. They have the AVAs inside them. very accessible, typically uncovered. There are some sports and work contexts where you're wearing gloves. Comparatively, though, to the feet, it's a lot easier to access and to use and interact with, especially in short bursts throughout activity. In the context of training and exercise, it's generally very accessible with some exceptions. And the face is a lot more difficult and disruptive to cool from. From a biophysical standpoint, it has great surface area to volume ratio, great thermal conductivity, lots of vasculature, rapid recirculation. In a state of heat stress, the palm really is the optimal anatomical location for heat transfer.